going to flow work is done by the fluid. That means the work, that is W dot is equal to, sorry, this is the W only. It is 135 kilojoules. It is 135. See here 135 kilojoules, and the rate of a heat loss. So what is that here? Uh, the total heat loss between the inlet and the discharge is 9 kilojoules of a fluid, right? So that is the heat loss between the inlet and outlet. So now you try to observe that, consider it as a Q, that is a 9 kilojoule per kg, 9 kilojoule per kg. So these things you should be more careful. That is, I think 9 kilojoule, 9 kilojoule per kg. So writing the steady flow energy equation, that is here you need to find out only the internal energy. That is if you take it as a U1 minus U2, then the equation is nothing but it is equal to P2 V2 minus P1 V1 minus P1 V1, right, plus C2 square minus C1 square divided by 2 plus G into Z2 minus Z1, Z2 minus Z1. And the important thing what you have to write is, this is D bar W by dm. See here, here it is coming as a D bar. Next, the another term is D bar Q by dm, D bar Q by dm, right? So this you should be more careful. That means this is, you can write this one as a you can write this one, right? So this should be very important over here, right? It is the flow rate. Now here what is because the flow rate here it is not mentioned in steady flow. 135 kilojoules of a work is done by each kg of a fluid, the specific volume of the fluid. So nowhere the flow rate is not mentioned. So the flow rate is not mentioned. That's why it is d bar w by dm and d bar q by dm, right? So that means finally when you make the calculation, that is substituting the value of P2, V2, P1, V1, right? Substitute the numerical values over here. Next, the kinetic energy at the exit, kinetic energy at the inlet section, right? Divide by, because all these things you have to make this particular things as in kilojoules. So that means here you will get it as a 2000. You will get it here as a 2000 plus the another one. This is also the 1000, because all these things here it is there 9 kilojoules. So that is 9 kilojoules of 9 kilojoules of so what is the work done here? This work done, it is given as 135. This work done is given as 135, right? Next, the heat loss. So it is here minus, the heat loss is minus 9 kilojoules. Heat loss is minus 9 kilojoules, right? When you substitute this minus of minus, that is here. Already one minus is there, and this heat loss. So this is heat loss 9 kg. That means this Q is nothing but equal to 9 kilojoule per kg. So this is what you have to apply. So after solving this particular case, then you will get the internal energy. Then you can get the internal energy, because if you here it is written as U1 minus U2. So internal energy decrease, that is what is the value? It is you after solving the numerical expression, then you can get it as a 20 point. You can get the value as 20.136 kilojoules. 136 kilojoule per kg, right? Kilojoule per kg. Then this is U1 minus U2. Then what about U2 minus U1? That is the specific internal energy increase. U2 minus U1, when you write it as U2 minus U1, the specific internal energy increase. Specific internal energy increase that you can expect. So this is how you have to solve the problem. So identifying the steady flow energy equation and what about the variables are given and apply that particular variables into that particular expression. So you will solve the, and these are all the things that are the solved problems from the PKNOC textbook, and you can also go through that PKNOC. So these are the solved problems. If you have any doubt, and you can go through the textbook. So the specific internal energy decreases by this one. Next, there is a heat exchanger problem. So there is a heat exchanger problem, and how you are going to apply the heat exchanger, because how many inlets are there? So the inlets are this one and this one. So there are two inlets are there and one outlet is there. So one outlet is there, one outlet. So how you are going to apply, because we have studied the steady flow energy equation already. So that is the steady flow energy equation. It is m1 dot plus m2. This is m2. This is m1 plus m2 dot is equal to m3 dot. This is m3 dot. This is m3 dot. Then apply the steady flow energy equation. So in this case, that is when you apply the steady flow energy equation, that is m1 dot into the enthalpy here. The certain water heater operates under steady flow conditions, receiving 4.2 kg per second. That is mass flow rate is given 4.2 kg per second of water at 75-degree temperature. Enthalpy is also given, right? The water is heated by mixing with steam. So here this is the water, this is the water, and this is the steam. Water and steam are mixing and supplied to the heater at a temperature of 100.2 degrees centigrade, and enthalpy is 2676 kilojoule per kg. The mixture leaves the heater as the liquid water at a temperature of 100 degrees centigrade, and enthalpy is 419 kilojoule per kg. How much steam must be supplied to the heater per hour? So how much steam? This is what you have to calculate. How much steam that it must be supplied to make the calculation. So apply the steady flow energy equation. What is the steady flow energy equation? Because here the enthalpy terms are there, so directly I will go for the enthalpy. Otherwise, I can go for the internal energy and flow work. So enthalpy, that is the H is equal to U plus PV. So U plus PV. If it is there, then H1 is equal to U1 plus P1 V1, right? But here directly I can use the H1 plus C1 square by 2 plus GZ1 plus GZ1, and here that is some heat, that is d bar q by dt, d bar q by dt, plus the second case m2, right? H2 plus C2 square by 2 plus GZ2 is equal to the outlet section. So that is nothing but equal to the outlet section M3 dot into, here it is H3 plus C3 square by 2 plus GZ3 plus d bar W by dt, d bar W by dt. This is the steady flow energy equation for this particular heat exchanger. Then, after, because there are no kinetic energy terms and the potential energy terms, so that one has to understand from this particular problem is that This is 0. This is 0. I think the heat transfer terminologies are also 0. So this is also 0. Heat exchanger, if it is a perfectly insulated, then there is no heat exchange. And this is also heat exchange is 0. So finally what you will get, M1 H1 M1 H1 plus M2 H2 is equal to M3 H3 M3 H3. So M1, that is this is the water. So that is M1, which is it is mentioned as a 4.2, right? H1 water at 75 degrees centigrade and enthalpy is 313. Enthalpy is 313.93 plus M2. This is now you have to find out the steam. So this one you have to find out the steam into H2, that is the steam, that is here it is mentioned supplied to the heater at a temperature and the enthalpy is 2676 is equal to M3, and here both the things are going to come here, that is both the things are, the flow rates are going to come here. So that is nothing but equal to 4.2 plus W2, or that is the M2. So M3 is nothing but equal to M3 dot is nothing but equal to M2 plus M1 dot into H3. So that enthalpy here, the temperature leaving the that is 419. So if you observe all these cases, then you can easily find out the mass flow rate of a steam. You can easily find out the mass flow rate of a steam, that the mass flow rate of a steam is 705 kg per hour. 705 kg per hour. So this is how you can make the calculation. This is how you can make the calculation, right? So this is the heat exchanger problem, because in your syllabus there is a separate heat exchanger is also there as a application point, applications of a steady flow energy equation. So that's why this particular problem is also picked up. So that in your syllabus there is a turbine is there, next one is the compressor is there, nozzle is there, and the heat exchanger and the heat exchanger. So these are the things are there. So slowly, understanding the variables and going through slowly, so that you can get the good concepts in this thermodynamics point of view. So slowly you have to understanding the problem, whether the given problem is a closed system problem or open system problem, that each and every student has to understand this particular case, right? So that is the third one. Next, fourth one. So this is the fourth problem, and here the 10 kg of a fluid, here it is mentioned that 10 kg of a fluid per minute, that is mass flow rate is mentioned. 10 kg of a fluid per minute goes through the reversible steady flow process. The properties of a fluid at the inlet is given P1. This is the density. Rho1 is nothing but density, 26 kg per meter cube. Inlet velocity 110, and the internal energy is also mentioned. And at the exit P2, Rho2, C2, and UT is mentioned. During the passage, the fluid rejects. See here, during the passage, the fluid rejects 55 kilojoules per second, or you can call it as kilowatts, and rises through 55 meters. So determine the change in enthalpy, and second one is work done during this particular process. Work done during this particular process. So how you are going to solve this particular case? First thing is try to find out the change in enthalpy. Try to find out the change in enthalpy. What we know that the change in enthalpy, that is this change in enthalpy delta H is equal to, that is the delta U, that is delta U plus delta of PV, that is the flow work, that is of this one is the flow work. So this delta PV, find out the delta PV. So how you are going to find out that one? That delta PV is nothing but equal to P2 V2, that is the specific volume, P1 V1, P2 V2 minus P1 V1, right? So reciprocal of the specific volume, see this one, right? So you need to focus on to this particular step. Then how you are going to write? That is P2 by rho 2, that is density of the fluid. Reciprocal of the specific volume is nothing but density, or reciprocal of the density is nothing but the specific volume. So P1 by rho 1, P1 by rho 1. And here the pressures are already given. P2 is nothing but equal to 5.5 bar. That means the 1 bar is nothing but equal to 10 to the power of 5 Newton per meter square. And density rho 2. So here this is also 5.5 kg per meter cube minus P1. P1 is 1.5 bar, 1.5 into 10 to the power of 5 Newton per meter square divided by the rho 1 value. It is 26. Rho 1 value it is 26. So when you solve this particular thing, you will can get the flow work. So you can get this particular flow work as 94.23 kilojoules, right? And later, let you call it as a kilojoule per kg. Because the already flow rate is given, that we will look for the next time. Next one is find out the delta U. That this delta U is nothing but equal to U2 minus U1. What is U2 here? U2 is